How about a woohoo because the professor's here? All right. I'm hot. Sorry. No more, and you don't want more, believe me. Okay, so sorry, I had to run back to get the power cord. Okay, so yeah, we're going to do induction. Okay, so the principle of induction means you start somewhere at P0, you prove a statement, and that statement is a predicate, P, which takes a natural number as an argument, right? It's like a program, right? It's a statement with a program, and that program either evaluates the true or false, right? So P of 0 is the statement with 0 plugged in for that natural number. And now it says if for every n in the natural numbers, the P of n implies P of n plus 1, what is the statement? Is the statement true for all natural numbers? Yes. Okay. Right? That's the principle of induction. Is all you need to do is those two steps up there, and then you've proven the statement for all natural numbers. How is the sound? Is it okay? Okay. Yes for 0, and we can conclude 1, right? We can just plug in 0 into P of 0, and then we see that P of 0 implies 1, and so on. Okay? Last time, some people asked, aren't you starting with the statement to prove the statement? Am I? No. Okay? So in general, for all n in n, P of n is not equal to P of n plus 1, right? P of n is a different statement than P of n plus 1. You fix n with the for all, right? And then you bind it, and now you have n and n plus 1. Those are two different things. So when you plug them into the statement, they're two different statements, right? Here's an example. P of 2 is this statement. It's syntactically this statement. P of 3 is this statement. Okay? There's some math nerds will go and say, well, they're just both true, so they're equivalent statements. But that's syntactically, they're different statements. Okay? Okay, so for all n and n, P of n implies P of n plus 1. Start with the statement P of n and prove P of n plus 1. What you've done at this point, it's a little still strange because there's still this free variable n. Okay? But you're sort of binding it at the beginning. And it's not free in the second statement. It's free. You take for all n, and you fix n, and now n is some natural number. And n plus 1 is a different natural number. Okay? A little subtle. You bind n in the for all n. But then after that, n plus 1 means something different than n. Okay? And so on. We did that now, in some sense, when we make this statement, when we prove P of n implies P of n plus 1, we have to use, now n is a variable, right? And it's a variable representing a natural number. So when we make our argument, we have to use arguments that work for any natural number. Right? We did this before with A divides B and A divides C implies A plus B plus C. The proof of that was this, right? You said both B and C are multiples of A, and you add them up, and therefore you get a multiple of A. Right? It didn't matter which natural numbers I used there. So in some sense, I'm proving many statements for all the natural numbers A, B, and C. Right? But I'm really sort of just because of the properties I'm using here, the distributive property here holds for all three, for any three integers. Okay. Okay, so now another question that people asked last time was, can you do induction over the reals? And the answer is no. You can't. Okay, because the key here for integers is again, I have my biggest number is 100, and you'll say 101, and I'll say 102. We can keep going, right? We could do this before the internet. This is what we did to entertain ourselves with our friends, right? Okay, and then somebody would say infinity, and then it would be over. Okay, but infinity plus 1, I guess, was the next statement, but then that was when it generally ended. Okay, so yeah, again, this is a statement, right? If you have the principle of induction is nothing more than the integers or the natural numbers. There's the next one. If you say something is true about 0, then 0 implies 1, you get that statement, and so on. Right? If something is true for P of n, it's true of P of n plus 1. We don't need to play this child's game, right? It just goes forever. We know where it's going to go forever. Okay? Okay. Right. That is your favorite example of natural numbers. Oh, we'll do that later. Okay, so the child Gauss, again to review last time, he showed this. He showed this equality for all natural numbers. What's the proof? Again, here he's assuming a predicate, P of n, and I sometimes switch n to k just to make it clear when what's n and what's what I'm inducting over, but it's not that important. I think it can be confusing for students, but I just tend to do that on occasion. So P of k is this statement, right? I'm just plugging in k for n, right? I'm not doing anything really, right? But I'm just sort of, it's a syntactic statement, okay? P of n is true for n plus k. What is that statement? Now you just plug in n plus k plus 1 into n, and what we have is this predicate here, this expression, the left-hand side of this predicate up there. The sum from I equals 0 to n, in this case n is k plus 1, and so I write it out, and then when I simplify it, I use the induction hypothesis. I get to use the fact that P of k is true, okay? So therefore, I see this expression here, whose left-hand side is over in that other inductive statement, and whose right-hand side is this other thing, which I replace it with. And then I just do the algebra. And now I see... Now, maybe I want to now make the argument again for k plus 2, but do I need to? No, I could just think of k plus 2 as, it's just a change of variables, right? You just change it all. It all works. Okay? So P of k implies P of k plus 1. Is this a proof? It shows that we can always move to the next step. What else do we need to do to prove it? Are we done? And we have to start. So we have to prove this statement at the base case. Okay, you have to get on the ladder somewhere. Yeah. Yeah, it could be, but does it where? I equals... I don't see what you're talking about. Where? Is it here? Oh, yeah, that should be, yeah. Oh, yeah, that's fine. Yeah, 0 doesn't make a difference, but yeah, okay, so that's fine. Sorry. Okay, yeah, it's the same expression. It doesn't matter, actually, in this case. I mean, the left-hand side sort of has to start with 0 because you want to get syntactically the right thing, but in the middle, it's the same thing. P of 0 is true, so plus inductive step gets you P of 1. And then you can say, look, I can go from P of 1 to P of 2 by plugging in k equals 1 into this induction step. I know that it holds for all k, and I can get to 2, and so on. Okay, we saw this last time. Okay, so it's true for all natural numbers. And it really is true exactly for that reason this child's game goes on forever. Okay? Okay, so let's do another induction proof. Okay, for every n in n cubed minus n is divisible by 3. Okay, in our notation, 3 divides n cubed minus n. What's the proof? Okay, we're going to do it by induction. So we're going to start with the base case, which is P of 0, and plug in 0 where n is, and say that 0 cubed minus 0 is divisible by 3. And it is, right? 0 times 3 is 0. Okay? For all k and n, P of k implies P of k plus 1. The induction hypothesis is that we're going to start with a k. Okay, so it says k cubed minus k is divisible by 3. That's what the induction hypothesis says. I'm just plugging in k for n. Okay, and now I'm going to use our definition of divisible as k cubed minus q is 3q, right? When we write proofs, it's often convenient to have equalities, right? So now we say we have this fact. That's what divisible means. Now you have, I'm going to try to prove that k plus 1 cubed minus k plus 1 is now divisible by 3. So I'll start with that expression, and I'll multiply out, and you get some various things. I simplified. Okay, so now here it's like a bit of a mess, and what should I do? Well, I kind of want to use the induction hypothesis, and I want to get 3's around. Okay? So what I do is I build the induction hypothesis in by minus subtracting k, because there's the induction hypothesis is the fact about k cubed minus k. So I just subtract k. And when I subtract k, I have to add k. So now you see, right? You see 3's everywhere, right? So I subtract k and add k. Okay? The 2k becomes a 3k. Okay, and then finally, I use the induction hypothesis. It's all in blue here. K cubed minus k is equal to 3q, and now we're essentially done, right? So it's the undistributive property of addition over multiplication. So we have this expression, and it says we know that k plus q plus k squared plus q is an integer because they're closed under addition. All right? Okay. So this is sort of the form. So that implies that this is divisible by 3. We've shown that for no matter which natural number k we started with, the property p holding for that natural number k implies that property p holds for that natural number k plus 1. Okay, what's that? USA. Okay. Yeah, it's colored. Okay, so any map can be colored with 4 colors, so that regions that share an edge have different colors, right? So if they're next to each other, they have to have different colors. Now here, actually this one it works, but you can see the 4 corners there. Those did not have to have different colors, right? That's for coloring. It's not required that these have different colors. Is there another corner where they have the same color diagonal? I don't see one. Okay, but this point, I could have colored this a different. I could have colored. Well, I don't see how to do it, but what is this state? What is this state? Yeah, they could have had the same color. Okay. States connected at a point can have the same color. That's important. Okay, that's what I wanted to illustrate. Okay, which states are here at this point? So that's Utah and New Mexico. What are the other 2? Yeah, okay, we get a little geography in too. So, okay, good. So now we're going to do a 2-color theorem. We're going to take the plane and divide it up into pieces. And the way we're going to do it is we're going to draw straight lines. So this line, you have to envision it going off to infinity in each direction. And there's the upper half of the plane and the lower half. Okay, so there's 2 regions here, right? When you add this plane, you add this line, you cut up the plane into 2 regions. This one, you've now cut it up into 4 regions, right? Does that make sense? Okay, and so here you cut it up into more regions, right? So you took some of the regions and you cut them into 2. This used to be one semi-infinite region, and now it's been cut into this triangle and another infinite region. Okay? Does that make sense? Okay, so this is building a map, right? Now we have a map, and now I claim it can be colored with 2 colors, properly colored. Okay? So is that properly colored? Yes. Okay, so there's your proof, right? It must be true for all maps now. And in fact, what you can see is we're going to prove this theorem, but let's just try to prove something along the way. First of all, what is a proper color? Okay, so a proper color means that when you draw these lines, there's line segments and rays that result. Right? There's natural line segments here, right? This dotted line is a line segment here. You can't see it. You'll see it on the next slide, hopefully. And that line segment separates two regions. On the one side is one area, connected piece of the plane, and on the other side is a different connected piece of plane. Now, those connected pieces of the plane have a color associated with them when in a coloring, okay? And they should be different, okay? So what you want to say, a proper coloring, is that says for every line segment, you look at the color of the region on the right and the color of the region on the left, and you say they're different. Okay, so I'm just translating this proper coloring into some fairly precise particular statement about each line segment. Okay, does that make sense? Okay, the same thing as I said, A divides D means that D times Q equals A for some integer K. So I'm just saying what a proper coloring is, you look at each of these line segments or rays, and you look at the two regions on either side, and they must be different colors. Okay, now swapping red and blue gives another valid coloring, right? So what does valid mean? For each line segment or ray, any two regions of the plane that are separated by the ray or line segment are different colors. Okay, so here's our picture again. So we're going to look at each line segment, or in particular we'll look at an arbitrary line segment, and we'll see it here. And we see that if one side is now blue and the other side was red, they're different. Now if we swap red with blue and blue with red, they'll still be different, right? So that's what we're saying, right? Swapping still makes it a valid coloring. Okay, does that make sense? Okay, good. Okay, so let's prove it. So the base case is maybe one line. You could color the top one red and the bottom one blue. That's fairly easy. Okay, you can add a line, and now what happens is this line cuts some regions into two, okay? And that region had a color. So what we do is we just keep both regions and make them both have the same color, okay? So how is this? Is this good? Is this a proper coloring? Well, it's proper, sort of. It's proper with respect to this line, this ray, right? It sort of has some nice properties. It's proper where it was proper before. Right? So according to this ray, the guy above is red and the guy below is blue. So the region above and the region below are different colors, so we're okay. Here too, for this line segment, we're fine. So anything that was a subsegment of a previous line is fine. Both sides of it are fine. Right? It's proper with respect to each line segment that we any line segment that is a portion of a previous line. Now, there is a problem, obviously, right? You see this new line, you've cut this region into two, and they're the same color on both sides. That's just how you did it. You colored them both the same. You just let them inherit the color. So what should we do? Right. So we look at one side of the line, and now we swap the colors. Now, this is not exactly what we did before. We didn't swap all the colors, and we didn't start with the proper color. But what we did on this side is we know that the coloring was proper with respect to all line segments from previous lines on this side. Right? Now, swapping them, that same argument about each line segment says, oh, every line segment on this side is fine if we swap. Okay? And clearly the line segments on this side of this half plane are fine because we haven't changed anything. Right? The regions have the same colors as they did before. Okay, and now finally, the switch fixes the conflict. Now we have to argue for each line segment, which is part of the actual line you added, that it's good. And it's good because it was bad, and you switched one side. So now it's good. Okay? And you can keep doing this, right? So which side should we swap? Who wants to swap upper? Okay, we'll swap upper. Okay, and you see it works. Okay, but the argument is I just talked about every line segment that existed before and every line segment that we created with the new line. Right? Yeah. The proof is the argument. The proof, he's asking where was the proof. The proof was this argument that I made about each line segment. right? I defined a proper coloring as saying all these line segments have a certain property. I argued that all these line segments have that property. Okay, so algorithm gives P of k implies P of k plus 1. Now, P of k is the number of lines, right? You know you had a proper coloring with k lines, and now I showed how to... And this one is very nice. I mean, in some sense, what does this also give you? Give you an algorithm, right? Give you an algorithm to color. I think this is in my eye. Sorry. Okay. Okay, so this is nice. For computer scientists, induction is really what we do. It is recursion. Okay. Okay, so now we're going to do something here. The sum of the first n odd numbers is a perfect square. Okay? Okay, the kth odd number, I'm just going to sort of write down this with expressions so I could really reason about it carefully. The kth odd number is 2 times the quantity k minus 1 plus 1. Okay? Okay, so the base case is the first odd number is 1 squared. So it is the sum of a perfect square, right? 1 squared is 1 is a perfect square. Okay, now the sum of the first k odds is a perfect square. Let's call it a squared. Okay, that's what we're saying. If I add 1 plus 3 plus 5, what do I get? I get 9. That's a perfect square, so a would be 3 in that case. Right? Okay. Okay, so let's prove this theorem by induction. The k plus first odd number is 2k plus 1. I'm just sort of using this expression up there just to make sure I have it all well organized. Okay? So that's what it is. We know that the sum of the first k plus 1 odds is a squared, right? The sum of the first k odds is a perfect square, and it's a squared, right? So now we have a squared plus this other next odd number, which is a squared plus 2k plus 1. So I went ahead and used the induction hypothesis. Okay, and I didn't just write the expression, I skipped a step here. Okay? Now what do we do? Is that a perfect square? Well, it actually, is it? It is a perfect square, but it's hard to see how to argue it is, because it would be fine if k was a, right? But, right? I mean, you're probably thinking it's a perfect square, but the k and the a are different, right? Or possibly different. Okay? Okay, so what do we do? Yeah. Okay, so what we do is we try to prove something that looks harder. Okay? So the sum of the first n odd numbers is n squared. So not only are we saying it's some perfect square, we're saying it's this perfect square. So it's a stronger theorem. Okay? So now we have to prove more. We don't have to prove just that it's some perfect square out there. We're going to prove the form is exactly n squared. Right? Okay. So now, on the one hand, it seems like, oh, now you're proving something harder, but what's good about that? What's good about having something harder to prove? Yeah. Right. I mean, in some sense, it's doing what some of you already noticed, that if the A and the K are the same, you're good. Right? And he's making it very particular to this problem, and that's true. But and that's what that's saying is that what you get to assume is something a bit more. Not only do you get to assume that it's a squared for some a, you get to assume that it's actually k. Okay, so you get to assume more to prove the next step. So that's where the power comes from. So now we're going to say the sum of the first k odds is a perfect square. It's this one. Okay? And now, when we do this proof, as we do in the induction step, we have a more powerful statement to use, a more specific statement, that a squared is equal to k squared. Okay? So the sum of the first k plus 1 odds is now k squared plus 2k plus 1. And now it's that triviality that you might have thought you saw before, but now you actually do see. Okay? You saw the future if you saw it before. So, good. Okay? Okay, it is, and that's P of K plus 1. It says the first of the sum of the first K plus 1 odds is K plus 1 squared. And we've concluded that. We began with the sum of the first K odds is a perfect square, is K squared. And we concluded that the sum of the first K plus 1 odds is K plus 1 squared. Yeah. It's stronger. Here, I'll give you another example. Yeah. Here, the specific, when you're more specific, it is kind of stronger. Okay, but it is more specific in this case too. But you have to prove something that's more specific too, right? So you also have to prove something that may a priori look harder. Okay, so let's use these tiles. We're going to tile Corey Hall. We only have these L tiles. This is what is this courtyard? It's 4 by 4, right? 2 to the 2 by 2 to the 2. Okay. So we can tile it this way. Let's put that there. Let's put that there. Let's put that there. Put that there. Voila. Okay, we have a little spot sort of fairly close to the middle where we can put a tree or something, or a plant. Right? Okay? So this is yeah. So what we did is we tiled a 4 by 4 square with 2 by 2 tiles, L tiles. Okay, meaning that one of the tiles is missing. One of those 4 tiles it looks like a shape L, right? 3 squares are there and 1 is missing. Okay? Okay, and we wanted this hole sort of to be in the center so we could put our tree there, right? So now the question is, can we always do this for this sort of pattern? Can we tile any 2 to the n by 2 to the n courtyard with L tiles? Okay, with 1 hole. We're going to leave a hole. Why do we have to leave a hole? Why do we have to leave a hole? Why can't we fill it all up? Okay, now I want to do it for every n. So this is going to be induction, but you want to think about why we want to have a hole? Why wouldn't we have 2 holes or yeah, I mean, I guess you will always have less than 4 holes, but maybe. Okay, so it has to have 1 hole. Why is that? Because the remainder of 2 to the 2n divided by 3 is 1. So you have to have at least 1. You can't actually fit them together. Any number of 3 times anything is not equal to 2 to the 2n. Okay? Okay, so it's true for k equals 0. So now you're picking 2 to the 0 divided by 3 is, well, I guess I should, 2 to the 0 is equal to 1, right? Oh, 2 to the 0 is equal to 1, so good. Okay. Induction hypothesis 2 to the 2k equals 3a plus 1 for some integer a. Again, I'm writing it as an equality. Okay. So now we're going to try to prove something about 2 to the 2k plus 1, quantity k plus 1. Okay, we want to say that it's a multiple of 3 plus 1. Right? That's what we're targeting. So now we can do the obvious things here, right? We know what exponents do. We multiply out the exponents and then you factor. You can factor in this way. If addition in the exponent is the same as multiplication with the same exponents. I just switched. It's commutative, and I took 2 squared. Now we can use the induction hypothesis, right? Now we see it, right? You can do the next step in your head, and then I'll show you. Right? That 4 is going to be a 3 plus 1. Right? Okay. So I guess I did it a dumber way, but it works. Okay? The 4 is the 3 plus 1. I wrote it that way. So 4 times 1 is the same as 4. 3 plus 1 is 4. And then I can factor out. So a is an integer, 4a plus 1 is an integer, and we're done. Okay? So this is just warm up. It's just saying, okay, well, we have to have one hole. Okay, so let's do this one. Let's tile the 2 to the n by 2 to the n squared to leave a hole adjacent to the center. If you have, let's start the induction at 0. I mean, you could at 1, just to make it easy. Then you have a 2 by 2 square, right? And you put in the tile, and there's one hole next to the hole is adjacent to the center of the 2 by 2 square. Okay. Okay, so now the induction hypothesis is that any 2n by 2 to the n by 2 to the n square can be tiled with a hole at the center. Okay? Now the induction step here, it's all set up for induction, right? You have 2 to the 2n by 2 to the 2n, and you know something about 2 to the n by 2 to the n. So what you get is this picture, right? You get that this side length, the whole side length is 2 to the n plus 1, and that's 2 to the n plus 1, right? And now you can divide each side in half, and you get a 2 to the n by 2 to the n courtyard, right? So, and you get 4 of them. Does that make sense? Okay. So the whole thing, the whole question is set up for induction, this induction. Sorry, I thought I turned that off. Here, let me do not disturb it. Sorry, I usually, never mind. Okay, so, sorry. I can't really work these things. Here, this is the old man's trick, is just, Google, please stop. Okay, so what do you do now? So this is what we have in the induction hypothesis. We can tile it. What I've drawn here is induction hypothesis. We can tile this one with the center hole. That's what we're allowed to assume. Right? Okay, what do we do now? What? Yeah, so what do we do now? Can we put in I don't know how to proceed now. Right? Okay, so, yeah. So I wanted this hole to be next to the center because that's where I wanted my tree. But inductively, it doesn't give me much help, right? I mean, it's sort of nice, right? Because there are only 4 holes there. And it says, well, with a tile, I can cover 3 of them if they're all next to each other. They're clearly not next to each other, right? So there's a problem here. So what I'd like is to actually have these holes be wherever I like, right? That's what I want for my induction hypothesis. I'd like to say, in fact, not only can I tile this 2 to the n by 2 to the n courtyard and leave a hole in the center, I'd like to be able to leave it anywhere, and then I can put it in the center and nice things will happen, right? I'd like to build off something stronger. Okay, so a better theorem. So this is a better theorem. What I'm going to say is I want to be able to leave the hole adjacent to anywhere, or leave the hole anywhere, wherever. You point to the place and say, leave the hole here. I should be able to tile the courtyard where the hole is there. Now the designer can do whatever they want. Okay? Okay, so it's a better theorem. So it actually seems like it should be harder to prove this theorem. But with induction, it actually makes it a little easier because you have more structure to build up from. Okay? The base case is the find now. You have to see that you can put the hole anywhere, and you just change the orientation of the L, and you can put the hole anywhere you like, right? You just rotate the L. So the induction hypothesis said it can be tiled with a hole anywhere. So we do the same thing we did before. And now I'm just presuming that what I want to prove is somebody pointed to this spot and says, put the hole there. Okay, it's an arbitrary spot. They could have pointed anywhere and have it be there. Okay, and then what I do is I cut the tile, the courtyard into 4 pieces. And then I use the induction hypothesis in each. And in the upper left one, I put the hole in the lower right-hand corner, and the upper right one in the lower left-hand corner, and so on. Okay? Because I can now use this induction hypothesis on each of the sub-courtyards, smaller courtyards, and put the hole anywhere, and I can put all the holes over here in this corner. Okay? And now what do I do? Is it clear what to do now? Use an L tile. That's an L tile. Okay? And we're done. Okay? So it's sort of nice. Okay. So in this case, it wasn't here. In programming, it says that when you call a subroutine and the subroutine has more power, you can use more power over it. You could ask more of it. Maybe you can do better in your program. Okay, so that's what's going on here. Okay, so that was strengthen. Unfortunately, these have similar names, but they mean something different. But I'll describe what strong induction is. But strengthening the induction hypothesis, strengthening the theorem, you're really strengthening the theorem. You want to prove some theorem, and it doesn't work out. Maybe you want to prove a stronger theorem. And with a stronger theorem, you can then use the stronger statements in your induction hypothesis to help you build up a proof. Okay, so that we saw that twice with the sum of the odd numbers and with the tiles. We use something stronger. We use something more about the inductive solution. Okay, so now strong induction. So that's called strengthening, not strong. But every natural number n greater than 1 can be written as a possibly trivial product of primes. So if it's prime, how do you write it as a product of primes? Yeah, itself and 1 or just itself. Okay, we're going to allow you to write it as itself. Okay? Okay. So a prime n has exactly two factors, 1 and n. Here we're going to start with n and we're going to break it down. Okay? So that's what a prime is. So if n equals 2, you could just write it as n equals 2. Right? That's already the product we're looking for. Okay, so now we know that n can be written as a product of primes. Now let's think about n plus 1. Right? We want to prove that n plus 1 can be written as a product of primes. Okay? N plus 1 is a times b, where a and b are between 1 and n plus 1. Right? It's either a prime or it's a product of something. Maybe primes, maybe something else. Okay? So if it's prime, you're done. You just write it again. If it's a times b, then what do we do? What we know is that n can be written as a product of primes. We don't know anything about a. Can it be written as a product of primes? All we get to assume in induction, or at least all we feel like we can assume, is that n can be written as a product of primes. Do we see n anywhere? We do in this n plus 1, but it's not useful there. It's really useful. What we want to do is we want to know something about a and b, right? Whether they can be written as product of primes. Okay? So P of n says nothing about a and b. It's just a property about n. It says n can be written as a product of primes, but it doesn't say anything about whether a or b can. So what we're going to do is invent a whole new principle, okay? Which is the same principle, but just for now, we're going to say if the principle of induction, the strong principle of induction, which is actually just the principle of induction, is that for all k, you get to assume p of 0 and p of 1 and p of 2 all the way up to p of k in your proof. If it's useful for you, you can assume all of these. You can use any of these facts, right? Because it makes sense that you should be able to use any of these facts because you're going up the ladder. And you know you went up every step of that ladder. So you get to use all the steps of the ladder in your proof. Right? Okay. So, and in fact, it's not hard to say that it is exactly the same principle as the regular principle of induction. But now we can use this property on all the numbers between 0 and k. And what is a? Is a a number between 0 and n here? So we can use the fact that a can be written as a proper product of primes. And we can use the fact that b can be written as a product of primes. Okay? So A and B. P of A says A can be written as a product of primes, and P of B says B can be written as a product of primes. Okay? So n plus 1 is equal to A times B. So you write down the product of A, and you write down the product of B, and now you have the product that equals n plus 1. Okay? So n plus 1 can be written as prime factors, or product of primes. Okay? Does that make sense? Okay, this is a very nice way to think of numbers, by the way. When we get to modular arithmetic, understanding that a number is just a product of the prime numbers that compose it is actually a very useful fact. Like this course does that. It builds up on itself a lot. So all the theorems we do now are going to be very useful in the next section. Okay, in a later section. Okay, so now there's something else that we often do, and we call it induction, but sometimes it's not easy to recognize as induction. Okay, it's called the well-ordering principle. Okay, let's think about the statement for all n p of n. Okay, if it's not true, there must exist some n where it's not true. Right? That's all. If the statement for all n p of n is false, then there exists some n where p of n is false. Okay? Okay, so now what we do is we can consider the smallest m with not p of m, and m is greater than 0. Just think about that object. If you have some predicate on all the natural numbers, the first one maybe that predicate, maybe it's true on 0, maybe it's true on 1, maybe it's false on 100, maybe it's false on 1,000, maybe it's true on 101. Just think about the smallest value of m for which it's not true, which is false. Okay? In this case, what happens is that what must be going on here is that p of m minus 1 is true. We know that p of m minus 1 is true, because this is the smallest m. We know that p of m minus 2 and so on. All of them are true up to this point. This implication must be false. Okay? So this is sort of an argument for the induction principle. It says that if for all n, p of n is, if it's not true that this predicate is true on every natural number, okay, there must be some place where p of n minus 1 doesn't imply p of n, or assuming p of 0. Let's say p of 0 is true. Okay? So that's just the contrapositive of the induction principle. If you put a not on, if you just switch the statements and not both sides, that is the induction principle. Okay? Okay, but the proof of this true, I said the induction principle relies on the integers. Okay, so the well-ordering principle also relies on the integers. It relies on this fact about the integers. It says that you give any subset of the natural numbers, there's a smallest element. The subset of the natural numbers we defined here, of interest here, is a subset of the natural numbers where p is false. Okay? Okay, but if this confuses you, don't worry about it too much, but it is exactly the same idea, it's the same thing, logically, as the induction principle. Okay, and it also follows from our definition of natural numbers. Okay, so you can do this argument over other things like rationals. Okay, you just have to define your ordering. We have a very natural ordering for natural numbers. That's why they're the natural numbers, because the ordering is natural. That was a joke. But in rationals, this could be like the smallest. We use this sort of notion of the smallest representation of a rational number. Okay? We being A over B. We had already done that to an extent. Okay? So with rational numbers, you could also order them. It's not the order you may think of, but there's ways to order them as well. Okay? Okay, so let's think about the well-ordering principle, and I'm going to prove something really cool, right? Okay, I'm going to say all natural numbers are interesting. Okay? Okay, so 0 is interesting, right? Who thinks 0 is uninteresting? Oh, no. But if you multiply something by 0, what do you get? Isn't that interesting? Okay. There's the proof. Okay. So, okay. So now let n be the first uninteresting number. So I'm just going to take some number n. It's uninteresting. Okay. But we know all the way up there, 0, 1, 2, up to n minus 1 are interesting, right? Okay. So n is the first uninteresting number. But being first is interesting, right? Thus, there's no smallest uninteresting number, natural number, right? There's none. So therefore, all of the natural numbers are interesting, right? This is the well-ordering principle, right? And here in the middle, you see the inductive state, the induction step. We say from n minus 1, n must be true. The fact that p of n minus 1, it is interesting. It can't be true that n is uninteresting, because it'd be the first uninteresting number, which is interesting, right? So I'm going to give you a break and let you ponder that. Okay, so I'll be back. We'll start again in a minute or two. Okay, good. Really, it's another phrasing of an induction argument. That's all it is, but it's what we often do. We're just like, okay, think of the first smallest counterexample and prove it can't exist. That's what we said. Okay? When you want to prove something that's by induction, you could do P of, use strong induction or regular induction and go up. But you could also say, look, there's no smallest counterexample. So therefore it must be true for everything. And you get to use the word smallest, and that's very powerful. Okay? You get to say there's a smallest. Okay? Which is really nice. Okay, so round robin tournament on n players. Every player plays every other player, and either P beats Q or Q beats P. Okay, no ties here. Okay, now here's a cycle. A cycle is a sequence of people, P1 through PK. where P1 beats P2, beats P3, beats P4, up to PK, but PK beats P1. So it's kind of problematic, right? We don't have in this particular thing, we don't know who's the best. Right? We understand what a cycle is? Okay, here's a cycle. Any tournament that has a cycle of length 3. Okay, so does this tournament have a cycle? Here's a cycle, right? No, it's in red. It's not a cycle. Is there a cycle? Is there a cycle? Oh no, my graph is wrong. Okay, well that's better. Okay, there's a cycle now? Okay, but now what does the theorem say? There must be another cycle. How long should it be? Do you see a cycle of length 3? Yeah. Okay? So that's what the theorem says. Those are all the definitions. You understand what a tournament is. You understand what a cycle is. You understand what the theorem says. Right? Okay. Okay. So what we're going to do is assume that the smallest cycle is of length k. Okay? Now, we have two cases. One's easy. What's the easy case? Can k be 2, first of all? They only play each other once, so there's no back and forth. So the smallest cycle has to be at least 3, right? So the smallest cycle, it could be of length 3. K could be 3. And then what are we? We're happy we're done, right? That case is done. Okay? Of length larger than 3. Now we're assuming it's the smallest cycle in this tournament, and there's no cycle that's shorter, right? That's what it means. Okay? Okay, so let's look at this cycle. We're just writing it down. This is pretty much how a cycle looks. There's no other way for it to look. There's P1 goes to P2. It's just an illustration of what it is, of the definition. Okay? And it's larger than 3, meaning that it doesn't just consist of P1, P2, and P3. There's more stuff down here, right? Because it's larger than 3. Okay, so case 1, P3 beats P1. So P3 and P1 play each other, right? That's what a tournament is. Everybody plays everybody. And when they play each other, either P3 wins or P1 wins. Here we're assuming that P3 wins. Okay? And now do you see something there? Do people see something here? Yeah, in this case, there's a cycle that's of length 3. So that's a contradiction to our assumption that the smallest cycle is of length k, right? So in this case, in the case that P3 beats P1, there's actually a 3 cycle. Okay? So that says it can't be that the length, in this case, if P3 beats P1, it can't be, it's all inside of contradiction proof, so you've got to be a little careful, but there's a contradiction here, right? Okay. So what's the other case? Here P3 beats P1, what happens next? P1 beats P3. That's the other case, right? Either one has to happen. That's the definition of the problem. Okay? You see a k-1 length cycle? Do we see one here? It's just in blue, right? So now the length of this cycle, it's the same length as the old cycle without P2. Okay? And is that a contradiction? Yes. It contradicts the assumption that this is the smallest k where there's no cycle. This is the smallest k, this is the smallest cycle, right? We said k is the length of the smallest cycle, and I just showed you a cycle of length k-1, so that's just false. So what I've just shown you is there's no example, there's no smallest cycle whose value is larger than 3. So there's no counterexample. Okay? So this says that this is true for every graph. Okay? Okay, and since I gave you the tournament theorem, I like tournaments, so let's do another tournament theorem. Okay, so a round robin tournament on n players, all players with the same definition we had. A bunch of players, they all play each other. One person wins, one person loses in each game. So a Hamiltonian path is the path between people. It's just an ordering of a path where P1 beats P2, beats P3, beats P4 up to Pn. Okay? Like this is an example. 2 beats P1, 1 beats whatever, what beats whatever, beats 7, person 7. Okay? So this is an example of a Hamiltonian path. Okay. So every tournament has a Hamiltonian path. Yeah, that's not super obvious to me. This is true. Now I'm nervous. I hope it's true. Okay, but well, it's true for 2 vertices. 2 is just more fun as a base case. Yeah. Okay. Either 1 beats 2 or 2 beats 1. One of those is a Hamiltonian path. It contains all the people in the tournament, and it's ordered. Okay. Now let's think about a tournament on n+1 people. You just remove an arbitrary person P. You just take the tournament, you remove them. Do you still have a tournament on the rest of the people? Do they all play each other? Yeah, everybody wins. Every game, one person wins. So it's still a tournament and yields a tournament on it. I think I'm off by 1 here, but on n people. But okay. Okay, so on this tournament on n people, that should say n, but there's a sequence P1 through Pn that contains all the people. It looks like this: A to B to C. It just goes, right? By the induction hypothesis. Okay. Okay, if P is a big winner, now let's think about this person P. Okay, it could be that he's just better than everybody. If he's better than everybody, where should we put him and still get a Hamiltonian path? He beats everyone, right? He beats C and he beats everybody on the line. So where can we put P? At the beginning, right? If we put him at the beginning, now you have a Hamiltonian path where P is the first one, and then you have your old Hamiltonian path, right? So you could put him there. There's your Hamiltonian path. The big winner, okay? Okay. Now the big loser you can put at the end, okay? And now, if neither, what you do is you have this guy somewhere in the middle, right? It doesn't beat everybody, doesn't lose to everybody. And what can you do? You can scan from left to right. And you can say, does he beat A? If he beats A, what should he do? Just put himself at the beginning. Okay, if he loses to A and he beats B, where should he put himself? Between A and B. Because A beats him and he beats B and everybody else is fine, right? Okay. So that's the proof. Okay? Very nice, very cute. Right? So what you do is you scan along here until you find a place where you didn't win all your games. So some of these people you may have lost to, but all of these people you've lost to, and you've lost to this one in particular, so this guy points to you, and you find the first place where you've beaten this guy, so you point to him. So these arrows all go in the right direction. Okay. Okay, good. Okay, so now let me prove something that's silly. You guys seem to like these the best, but okay. All horses have the same color. Okay. It's true. If you have one horse, it's the same color as the horse. It's just a horse. A horse is a horse. The induction hypothesis, any K horses have the same color. Okay. So induction step is, we have K plus 1 horses, right? So I'm just indicating what they are by there's horse 1, 2, up to K plus 1. And now what I can do is I can apply the induction hypothesis that any K have the same color, and I can say the first K have the same color. Let's just say it's blue, right? It's some color. They're all the same. Okay? I can now I have these horses 1 through K plus 1. I could also use the induction hypothesis on any subset of K horses, right? So in particular, I'll use the last K horses, 2 through K plus 1. Say all of these have the same color. Okay? Okay. So now I want to say all the horses have the same color. Okay, well, you have 2 there, right? Is 2 the same color as 1? Yes, by the first line, right? All the horses 1 through K have the same color, so 2 is the same color as 1. And now is 2 the same color as all the horses 3 through K plus 1? Yes, by the second line. 2 is the same color as 3 through K plus 1. Okay? So that says they're all the same color. Right? Okay. Okay. We know horses aren't all the same color. Yeah. In this last one? Okay, so what I said, 2, in the second line here, look at 2 is blue and K plus 1 is blue. Right? That's what I argued. The fact that 2 and K plus 1 are both blue is something I can conclude from the induction hypothesis that this last subset of K horses have the same color. Right? 2 has the same color as 3, has the same color as 4, has the same color as 5, up to K plus 1. Every one of those horses in that set have the same color. Okay? So now I'm using this twice. I'm using the fact in the last step, I'm saying 2 has the same color as 1 because of the first line, and 2 has the same color as all of those because of the second line. So they all have the same color. Yeah. Right. Yeah. Yeah. There's yeah. So this proof works when K is 2. It actually works almost everywhere. P of 2 implies P of 3. P of 3 implies P of 4. P of 1 is what we started with. We need to start at P of 1 and make sure that implies P of 2. Okay, so let's check that. Okay, clearly it's not going to work. Because if it worked, we would be done, really. We would have a proof. Okay, that's where we made the mistake, right? Let's see if this argument works for P of 1 implies P of 2. Okay, 1 has the same color as itself. 2 has the same color as itself. There's nothing in common. Right? So therefore, this argument fails right at the beginning. So one little place in that ladder is broken, that's it. Right? It's just not true. And it's clearly not true, right? We know that all courses don't have the same color. Okay? Yeah. No, I'm not. In this one, I'm not using P of K plus 1. In the previous proof, no, I didn't, because I only used the last K. I didn't use the last K plus 1 horses. Right. Right? Right? I didn't color the 1 blue. Okay. He's just asking, here, he was worried that I was already using the K plus 1 theorem to prove the K plus 1 theorem, but I'm only using it on K, so that particular argument is fine, even though the whole thing is ridiculous, right? Okay, so that's a problem. Okay, that's fine. We can extend our so the problem is that the base case is wrong, or something about the base case. So we can fancy up the base case, obviously, right? We just fix the base case and say, the new base case is there are 2 horses with the same color, right? That's fine, right? And then we could run the proof, right? Because we only needed 2 to get a horse in the middle. We can get to 3. But, so there are 2 horses of the same color. Okay, well, it still doesn't work. Why doesn't it work? This theorem needs to argue for any set of K horses that are the same color. Right? That's what I used in this proof. Okay? There are 2 horses is not for all 2 horses. Well, I was given an arbitrary set of 3 horses, and I picked 2 of them and said they must be the same color. So I'm using the notion that for all 2 sets of size 2, the horses have the same color. And that's not true as a base case. Okay? Yeah, well, we know this is all easy, right? We know it doesn't work, but it's much more subtle when you're trying to prove your theorem and you write stuff, and then we're going to tell you, well, that's not a proof. Or we may even write stuff and you could tell me it's not a proof, right? Sometimes there's bugs. And it's much harder to understand what arguments are in true theorems, because essentially there's a level of trueness around, right? So, but still, okay. So let's talk about one more induction. Okay, it's a puzzle. It's Terry Tao's favorite logic puzzle. Terry Tao is a Fields medalist, and amazing in many ways. Okay, any islander who knows they have green eyes must do a bad ritual that day. I'm not going to say what the bad ritual is. No islander knows their own eye color. Okay, so they either have blue eyes or green eyes. It's a Scandinavian island. All the islanders have green eyes. So this is very sad. They're all supposed to do the ritual, right? Because they all have green eyes, so they have to do this bad thing. Okay? This is a problem, right? Already this is a problem, right? Nobody wants to do this. So what's the first rule of the island? You don't talk about eye color, right? Did you guys see the Fight Club? Has anybody seen the Fight Club? Yeah. First rule. Okay, don't talk about eye color. And you can see why they don't talk about eye color, right? They can all see all these people have green eyes. They don't look, no mirrors. The mirrors are like not good, and there's lots of waves, so there's no mirrors. Now somebody visits the island and says, "Hey, I see someone has green eyes." So he's told them nothing, right? Because they all see that somebody has green eyes, right? On day 100, there's 100 people. On day 100, they all do the ritual. Okay? Why? Well, the problem is they know induction. So here's a case where induction's not good for you, apparently. Okay? So, too much knowledge, right? Okay, so, what are they trying to do? They're trying to figure out whether they have green eyes. Everybody doesn't see themselves, right? They only see other people. But somehow they all know on day 100 that they have green eyes. Every one of them knows themselves that they have green eyes. Okay? That's what has to have happened. Otherwise they wouldn't have done the ritual. Okay? Does that make sense? All right. Okay, so the theorem is if there are n villagers with green eyes, they do the ritual on day n. Okay, after the visitor visits and says this thing. Okay? Okay, if n is equal to 1, is this true? Is this statement true? Right, what do I see if I have green eyes? I see everybody else has blue eyes. A visitor came and said, "Oh, I see somebody has green eyes." It must be me, right? So I'm done. Right? I have to do what I have to do. Okay? Okay. So now the induction hypothesis is that if n people with green eyes, they do the ritual on day n. Okay, so do you see the step? So what happens is if they didn't do the ritual on day n, and I have green eyes, what do I see? If I see n people, let's say I see n people with green eyes, and they don't do the ritual on day n, what do I know? Right, because the theorem tells me they did. If there's n people there, I see they all have green eyes, and they didn't do the ritual, so there must not be n people with green eyes. There must be n plus 1. Right? It can't be n plus 2 because the only person I can't see is myself. So there must be n plus 1. So on the n plus 1 day, what must I do? I have to do the ritual. Right? Okay, so a green-eyed person sees n people with green eyes. He knows on day n they didn't do the ritual. And so there must be n plus 1 needed people with green eyes. Okay? That was sad. Right? Okay. Wait a second. This doesn't make any sense, right? It makes no sense. It's like the horses thing. It's not. This is actually fine. It's a valid induction. The visitor added no information, right? There were 100 people. They all knew somebody had green eyes. What did they add? Right? Okay, so it's sort of there's this notion of common knowledge. It's like I know what other people know, what I know that they know that this is all going on, right? You see this happening. If all those other people knew this, they would have done this to themselves, right? So on day one, everyone knows everyone sees more than zero, right? On day two, everyone knows everyone sees more than one, right? I know that everybody sees more than one. I see that, not only do I know what I see, I know that everybody else knows this fact, and so on. That's the argument here. Okay? So, on day 100, because on day 100 you see 99 others, and those 99 others didn't see 98. Right? And so on. And you just induct backwards, right? Okay, so it's sort of like the Emperor's New Clothes. The interpretation of the logical interpretation of the Emperor's New Clothes is funny. But I have to say this means something, right? What it means, in some sense, there's this thing that mathematicians do. Here, just a second. They don't just say anything. They just look at each other, and one of them grunts, and then they start doing induction. Okay? Because you can reason, right? Like when we have arguments, it's the same thing. If we argue with our friends, we know what they're going to say. We don't need to. We could just do induction. So it's sort of interesting as a notion of communication. Anyway, see.
Question about induction in general, like what we already know, we prove it by induction. But could we prove something from scratch by induction? Like Gauss already knew that formula, n plus 1 over 2, and then he
is neither compare him with the short list.
No, you should compare him to the first person.
Yeah, if he's in the middle, can I say you don't mind? Okay. So I'm